So we're looking at another example of conservation of energy for kind of a gravity type question. And if we remember, for conservation of energy from the last video we saw, we could write that as 1/2 m times the quantity Vf squared minus Vi squared. So that's the change in kinetic energy equals, and this is the negative change in the potential energy, which is Gmm times 1 over Rf minus 1 over Ri. This is totally fine to do, and remember from the last video, the mass of the object that is moving here around that kind of planetary or sun figure doesn't actually matter. And this all stems from the fact that the change in kinetic energy is equal to the negative change in potential gravitational energy here, okay? So for this problem we do here, we could just go ahead and throw all of these values in to this red equation and go ahead and force things and solve them out. We're actually going to look at it in this way this time, kind of break the problem into a few different steps and solve it out that way. Same thing in the end, just a different way of kind of approaching it. So what we have here is a 250 kilogram satellite. It's to be launched from the surface of the Earth. So surface of the Earth, that's important. We know it's 250 kilos. When it reaches its max height, a secondary rocket will be fired to produce an orbit having a radius of 9.6 times 10 to the 6th meters. Because remember, if, here's the Earth, if you're on a shuttle or a rocket and you're just directly going off like this, you're just going to fall back down in a second. You need something to give you a tangential velocity to put you into that orbit there, which is why launching directly upward is a terrible way of getting into orbit. Anyways, that's what's going to happen in our problem. So here's our final radius here, the 9.6 times 10 to the 6 meters. If we wanted to, we could directly go down to part C and calculate the launch speed of the satellite just by using this red equation. Like I said a second ago, you're totally fine to use that. That's what we did in the last problem. It's just a lot of algebra. We're going to break it down this time into two potential energies and then use this equation instead, which is the same thing, but just kind of broken down so we can play with the numbers a little bit easier. Okay, so for part A, we're going to calculate the potential energy of the satellite on the surface of the Earth. Okay, and if we remember, gravitational potential energy is going to be negative Gmm over R for whatever our position is. And since we're at the surface of the Earth, that's just going to be the radius of the Earth there. This is going to be the mass of the Earth, and this is going to be the mass of the satellite. So at this point, we know all of our numbers. If we've got our solar system data sheet sitting around, we just need to shove all these in and get an answer. So negative 6.67 times 10 to the negative 11th. Mass of the Earth is 5.97 approximately, times 10 to the 24th kilograms. Mass of our satellite is just a 250 kilos. And then we divide by the radius of the Earth, which our sheet tells us it is 6.38 times 10 to the 6th meters. Okay, so we just shove all that in, we get a number there. Make sure that it's negative. We define potential energy as negative quantities. All the way out at infinity is where we define our 0 point. So everywhere inward of that is negative. And if we throw all these together, we should get here, let's see, 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24th times 250 divided by 6.38 times 10 to the 6th. We should get 1.5 times 10 to the 10th, and that's a negative. So negative 1.5 times 10 to the 10th joules, because that's an energy. Okay? If we'd like to do that for part B, but we're now in orbit, same equation, negative Gmm over R, where that's the mass of the Earth, that's the mass of the satellite. Now we are in orbit here, and that means that our radius has changed. Our orbital radius is going to be the combination of the radius of the Earth plus the altitude. If we think about the Earth here, here's the Earth, it has a radius, and then you go up some extra altitude. We need this entire bit here, so we need to add those together. So when we do this, we're going to have the negative, and then the G is the 6.67 times 10 to the negative 11th. Mass of the Earth is the 5.97 times 10 to the 24. Mass of the rocket is the 250, and then divided by, and then here's where we're putting the two things together. We're putting in 6.38 times 10 to the 6th plus, and then whatever our altitude was for the orbit, which Oh, actually, we didn't actually have to do that here. They actually give us the entire thing. It has an orbit having a radius of this amount. If they gave us an altitude, we'd have to add together. They didn't give us an altitude here, which is nice, because now we can just say, hey, we know what the radius is. It's 9.6 times 10 to the 6th meters. Okay? If they gave us an altitude, we have to make sure we added, but they gave us the radius of the orbit. Orbit. Words. So let's just shove these numbers together, see what we get. 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24th times 250 divided by 9.6 times 10 to the 6th. We get, about 1.04 times 10 to the 10th, and that's a negative number. So negative 1.04 times 10 to the 10th joules. Okay. To calculate the launch speed of the satellite now, we need to go use our change in kinetic energy equals the negative change of the potential. So our kinetic energy, and remember, deltas are always final minus initials equals the negative of the final minus the initial. So our final velocity, whenever the rocket, here it is on Earth, it gets up to some point, and when it gets up here, its velocity is 0, because then it needs to shoot sideways so it goes in a circle. So the final velocity is 0, which means the final kinetic energy is 0, which means this initial kinetic energy, we can just say it's minus, and then 1/2 m of the satellite v squared, where this launch speed is what we're looking for. This has to equal the negative of, the final minus the initial potentials. And if we take a look at this right here, whenever we're in orbit, that is our final potential energy. And whenever we're on Earth, this is our initial potential energy. So it's going to be the negative 1.04 minus the negative 1.5. So we can say here that it's going to be the negative 1.04 times 10 to the 10th minus the negative, so that's going to be positive in a second, 1.5 times 10 to the 10th. Okay? And I guess if we wanted to put in the mass of our satellite, we could. We know what that is. It's given in the problem. That was 250. So at this point, we just need to put all these numbers together and solve for that velocity right there. This is our initial launch velocity. So 250 divided by 2 is going to give us 125. So we've got a negative 125 initial velocity squared equals negative. And let's just put these numbers together. Let's be very careful about this right here, because the negative of my negative is a positive. So we're going to get negative 1.04, and since these are both times 10 to the 10th, we don't actually have to worry about it, but if we want to, let's do that. So negative 1.04 times 10 to the 10th plus 1.5 times 10 to the 10th gives us, let's see, that should be times 10 to the 10th. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 there. Okay, that's fine. This gives us 4.6 times 10 to the 9th joules. If you rounded this number or this number a little different, maybe this right here, what we just found, the 4.6, will be a little bit different for you. Maybe you'll have like 5 point something, whatever. It's just a rounding. We really care about the setup. And then at this point, we need to get rid of the negatives on each side. They're going to divide out. That's nice. Then we can divide by 125 on each side. Divide by 125. So divide by 125. And this gives us that the initial velocity squared equals 3.6, or let's just say 3.7 if we round that up, times 1, 2, 3, 4, 5, 6, 7, times 10 to the 7th. And then we need to get rid of that square, so we take the square root of each side, which gives us, just around 6,066 meters per second. Give or take, depending on rounding. It's somewhere around the 6,000 mark, depending on how I've rounded in this problem. I've got anywhere from 6,000 to about, I've gotten as high as 6,400 meters per second before, just by rounding differently. So that's why we really care about back of the envelope. If we wanted to do this very specifically, we'd have a computer crunch through it. But these are both good answers here. Somewhere around 6,000 to 6,500 is somewhere within the ballpark there. Okay? And that's just what we're looking at here. We did the same thing as before, where we did the 1/2 mv squared minus vi squared equals gmm over 1 over rf minus 1 over ri. We could use that equation to directly solve this, or we could just figure out what the potential is at the initial and final positions, and if we know that, we can just use the conservation of energy in this way to solve it. Some people find that this is a little bit easier to look at mathematically whenever they're going through these steps right here. I think the math was a little bit easier there than the last problem, but it did force us to do some math earlier on up here in order to get our numbers. So it just kind of breaks the problem down in different ways. Whichever way you like to do is totally fine. There's many ways to solve this out. But in the end, we're finished. That's conservation of energy. You all take it easy. Adios. Have a good one.